Welcome to this IHS Oil and Gas Technology online event. Fires and explosions represent the major safety concerns of the oil and gas industry. No other aspect of industrial safety receives more attention in the form of codes, standards, technical papers, and engineering design. Now, before this presentation, we'd like to invite you to submit questions at any point by using the Submit Question button at the base of this video console. Also, some of the presentations you will see today include detailed information, so we would encourage you to click the Download PPT button so that you can follow along with your own copy of the PowerPoint slides. Engineering Manager Bruce Bader is Phoenix Meccano's hazardous location expert. Bader has 22 years of professional experience involving mechanical design engineering, manufacturing engineering, and process engineering. He holds a U.S. patent describing a universal bracket designed for transmission solenoids. Bruce, welcome to today's event.
Thank you for the introduction. Again, today we're talking about protecting electrical equipment in hazardous locations. As you can see on the slide, some key objectives for today. We're going to look at a little bit of a historical overview just to give a perspective of where we're at. We'll give a little bit of fundamentals on hazardous locations and ignition prevention in those type of situations. We'll explain the difference between the newer class zone NEC 505 and the old NEC 500, which is class div, which most of us know very well. And then we'll speak about the various protection methodologies used in these various zones. A little bit of a historical perspective. This goes back hundreds of years, early 19th century. It was very common for coal miners to go down into the mines using torches and lamps to light the way. As they dug deeper into the ground, we ended up getting some buildup of methane gas, buildup of coal dust. Lamps and methane gas didn't play very well together back in the day, and they started to have a lot of mine explosions. What they ran into was, how do we overcome this situation? So their first attempt was, we were going to ask for volunteers to go down to the mine first by themselves with a torch to clean out the gas. Obviously, you'd think that after about the second or third time, the pool of volunteers ran out. So after that kind of went away, they came up with some various methodologies. They tried some different things without much degree of success. However, in 1815, a device called the Davy Lamp was introduced. This was a lamp that had a heavy brass mesh screen over it. And what they found out is that they could go into the mine. There would be enough light emitted through the mesh that they could kind of see their way and work in the mine. And that when the torch came in contact with the methane gas, the flame would not propagate through the mesh out into the atmosphere and create a larger explosion. So we can pretty reasonably recognize the Davy lamp in 1815 as our first hazardous location apparatus. Obviously, the advent of electricity, we've got a little bit more advanced than lamps and the old pitchfork and thing from the 1800s. And we'll jump ahead to the 1900s and kind of look at a brief timeline. We'll give a couple points here just for some reference. Some of these are relatively fixed, and a couple of them their dates are a little bit moving. So 1900s, we start talking about electric codes. In 1912 in Europe, the first standard for EX protection types were introduced. So we started to actually find how to separate different devices into different types in different areas. Jumping back over to the United States, we caught on to this in 1920, and the NEC came out with equipments in extra hazardous locations, which was the standard for hazardous location at the time. In 1928, in the United States, we started to come up with classifying materials. 1947, we came up with class and div, which is the NEC 500 that we all know and love. While that was going on, even during the Second Great War, they started to actually, in Europe, introduce rules for construction regarding electrical equipment in EX areas. So there was, even during time of war, there was a recognition that hazardous locations were dangerous, and we were trying to preserve the lives of the workers because we needed them for war material. You jump ahead a few more decades, you get into 1971 in the United States. We started to recognize the need for recognizing different operating temperatures of equipment. Different gases exploded or ignite at different temperatures, and we started to recognize the need to be able to classify that. In 1975, we started to see the first big push in Europe towards harmonizing some of the national guidelines. You can imagine in Europe, 25, 30 countries having 25 or 30 different standards made life a little bit difficult to sell product across borders. And the same thing goes more on a global scale with 200 plus countries in the world. That kind of ended in 1994 with the ATEX directives, EC 94-9. That was really the first unification of the European legislation for the European Union. In 1996, the United States kind of recognized the fact that the rest of the world was talking in a different language than we were, and we started to introduce the class zone, the NEC 505. And then I put a date out there. In 2007, IEC, some worldwide unification of guidelines. The IEC had been around much, much longer than 2007. But in 2007, we began to see the IEC 60079, the EN 60079, and the introduction of the UL 60079 begin to look more uniform and more harmonized. Some people have asked, and there is a drive to say we're going to have a harmonized world standard. Probably that we'll see something close to a harmonized standard, but I don't think we'll ever see a truly unified standard, as there's too many national differences in history going on. So we'll probably never see a completely harmonized standard, but we'll see something much closer. We talk about where we deal with hazardous locations. Obviously, the easiest thing to do is talk about the different industries. Some of them are very obvious. We talk about mining industry. We've already talked about that with methane gas, coal dust. Oil and gas industries, obviously, you have the flammable gases and liquids there during different extraction and processing. Different chemical industries, obviously, gases, liquids, solids all come into play there. Energy production, so we take the mining and the oil and gas industry stuff, put them together and turn it into energy. We're still dealing with the same gases, oils, coal that we have there. The painting industry, a lot of flammable solids and liquids. And then you get into some areas that maybe people don't necessarily think of but are just as important. So we talk about foodstuff industries, combustible dusts. Flour and sugar are two big ones, and sugar is an extremely explosive dust. You talk about agriculture, and you say, why agriculture? Well, biogas, methane gas produced from our cows and other livestock. We're now beginning to reclaim that and use that for energy production. However, it's still methane gas. We talk about recycling and disposal industries. Materials that will fall into the waste stream need to be dealt with, as well as metal processing. When you do welding, grinding, cutoffs, the metal fines sometimes are hazardous. They do ignite. We do have to deal with those. So really, when we talk about hazardous locations, we need to talk about ignition and combustion. When we start with that, we look at the fire triangle. You have to have all three sides. You need to have heat, you need to have fuel, you need to have oxygen in order to make this occur. You eliminate any one of those legs, and all of a sudden you don't have combustion, you can't have an explosion. So the whole principle behind hazardous location protection is to eliminate or minimize at best, or worst, the one of those three sides. So really, as I said, in hazardous location, the goal is to prevent ignition. You can provide it by three different methods. Side of the equation. Or the third method is really that if you can't eliminate the explosion, you limit the effects of the explosion into something which you deem to be acceptable. And that could mean different things to different people, but that's the worst case scenario. So really, the primary method is prevent an explosive atmosphere. It can be done several different ways. The easiest methods is we talk about ventilation methods. So where in a mining application, say, you're pumping fresh air into the mine to help expel the methane gas. You also have a lot of gas detection systems that are being used. So these monitors and systems that are out there being used, if there is a concentration of gas, whatever you're looking for or concerned with, is present and it becomes into a level that could be considered dangerous, you'll have these systems in place that'll set off alarms and allow you to deal with that situation. Another method that you do is you add inert materials to devices. A simple way to do that would be in a purge and pressurized type system where you pressurize the device with an inert gas like argon, which would prevent any of the explosive materials from coming in contact with the device, thus eliminating the explosion. The other thing is just to prevent introduction of combustible materials. Sometimes we call that housekeeping. If you don't have a buildup of materials, you can't have an acceptable limit that would allow an explosion to occur. The secondary measure that we talked about was avoiding ignition. Methods that you use there is you employ different protective measures against ignition. So you eliminate ignition sources. The next thing you can do is you classify materials, you classify areas, you classify devices so that you can determine what type of devices are allowed to be used in certain areas and with certain materials present. And then the third thing that you do is you define what your acceptable temperatures are. That gives you an idea of how much heat can be put into an area and keep your ignition points below the area that you'd have an explosion. So simply limiting heat, eliminating that leg. So we look at different ignition sources that are out there. Obviously from an electrical standpoint, which is where a lot of our devices are nowadays, you try to eliminate hot surfaces, maintain your heat rise to a minimum amount, keep the heat down, allow the different materials to be in contact with that device. You eliminate arcs and sparks, electrical arcs and sparks. How can you do that? If you eliminate those, you eliminate the opportunity for the heat or the ignition. Electrostatic discharge is an important concept in this, and you have to have special measures in place with your devices to prevent electrostatic buildup and electrostatic discharge, which could spark an explosion. Some other things that you need to deal with, maybe not necessarily with electrical devices, but atmospheric discharge, lightning, and how do you keep the static buildup from that, which is to the atmosphere. Mechanical sparks, so you need to use non-sparking tools in the area. Chemical reactions, open flame, obviously. Electromagnetic radiation and optical radiation. Not so much a key for today's conversation, but something you need to be aware of during your entire hazardous location planning. So one of the things we talked about in terms of the secondary measure was classifying materials. We'll break it down and keep it kind of simple. There's basically two classes. Class 1, which is your gases and your vapors. Class 2, which is your dust and particles. We can classify materials further from whether it's a gas or a dust into smaller groups based on, in terms of gases, your flash point, your ignition temperature, your maximum safe gap that's allowed in your device, as well as your temperature classes. With dust and particles, you end up looking at smoldering temperature, your ignition temperature, and what your minimum ignition temperature are. Different measures to determine how materials react in certain situations and how you can classify them by those in order to maintain safety. Next thing you can do is classify areas. Again, we'll break it down kind of simply. Group 1, mining industry. So anything that we're going to deal with mine gas or mine dust, any mine, Group 1. Everything else is Group 2. So any other area where you might have a hazardous atmosphere. We'll break Group 2 down into two separate subcategories or subdivisions, one being gas and one being dust. Obviously, they have different reasons. We move them into separate groups. And then we can even subdivide those into categories, and we'll call them Category 1, Category 2, Category 3. We'll touch on mining real quick. There's two different subdivisions in mining, M1, M2. M1, you allow the material, or you allow the device to remain energized when in presence of a hazardous atmosphere, and M2 is where you eliminate the energization of the device during introduction to the hazardous atmosphere. We'll break group 2 down a little bit more here. Remember, gas and dust are separate areas, and each area has 3 categories or designated zones. So the zones describe the amount and the duration of material that is present. So we have category 1, which is the highest category. We'll call that zone 0 for gas and zone 20 for dust. Why they decided to change it instead of having zone 1 and zone 21 so that we'd match categories and zones together, beyond my scope of comprehension, but that's what we have to deal with. So for zone 0 or category 1, we deal with concentrations are present continuously or for long periods of time under normal operating conditions. Then we break into category 2, which is called zone 1 for gas, zone 21 for dust, and that's where combustible concentrations are likely to be present during normal operating conditions. And then we have our least dangerous category, which is category 3, also known as zone 2 or zone 22 in dust, where the combustible concentrations are not likely to exist under normal operating conditions, and you'd only see them under abnormal conditions. One of the biggest issues we run into in the United States is the difference between class div and class zone. On this slide, we kind of break that down where Division 2, which is the least dangerous part of the NEC 500, would be equal to Zone 2 or Category 3 materials. And then Division 1 contains both Zone 1 and Zone 0. Under the code, the NEC Division 1 combustible concentrations can exist for some or all of the time under normal operating conditions. In Division 2, combustible concentration is not likely to exist under operating conditions. So you can see the parallel between classes and division as well as the class zone just by the terminology. So we can classify materials, we can classify areas, we need to classify devices because that would tell us where materials can be used. So each electrical device that's going to be used within an EX area needs to be EX approved or hazardous location approved. And each device is approved for use in a different category. So if you look at the chart here, if the category approval is 3G for gas, it can be used in zone 2. If it's 3D, if you jump down a couple, you can see that can be used in zone 22. Again, you go back to the gas side, 2G can be used in zone 1 or zone 2 because you can always use material at a higher category approval into a lower zone. And 1G can be used in any of the 3 zones. Dust is the same thing. 3D, as I said, can go in zone 22, 2D goes in 21 or 22, and 1D goes into any of the 3 zones. The other thing that you do when you're trying to minimize this is you define the temperature. So you look at your temperature, and what you do is you look at the maximum temperature of an electrical device, and it must always be lower than the ignition temperature of the gas that it will be near or the dust that it'll be near. So in gases, you're actually divided into 6 temperature classes, and they're given there on the right-hand side, T1 through T6. And conversely to that, your electrical devices are selected according to their maximum operating temperature, and they're to be placed in the appropriate temperature class. So an electrical device that would be a T6 would have a maximum operating temperature of 85 degrees C, which would allow it to be used in any of the temperature classes there because T6 is 85 degrees C. Here's a little bit different view of that temperature classification. And what happens is you look at the ambient temperature, the internal heating temperature of the device that you're looking at, and you look at the end result, which is the surface temperature on the device. And what you're looking for is maintaining the maximum surface temperature to be less than the ignition temperature of the material that you will be introduced around it. Same basic concept as before, a little different way to present it, and that's how it works. For most electrical devices, junction boxes and things like that, you will see charts that are available that'll tell you that you can have a certain amount of current at a certain voltage going into an area, and then it'll tell you what the limit will be for that current to be used for a certain temperature class. Different manufacturers have very similar charts. It's easily available out there and everybody can see it. Particular questions could be pretty well understood. And this is what it really breaks down to, and this is kind of what happens at the end of the day. You're looking for what are the acceptable protection methods to be used in the various divisions or zones. This chart breaks it down pretty succinctly. In the old class div system, you can use intrinsic safety, explosion-proof enclosures, or purge and pressurized devices in class 1 division 1. And in class 1 division 2, you can use hermetically sealed, non-incentive, non-sparking, and purge pressurized, but type Z only. In the class zone system, in zone 0, you can use intrinsic safety, specifically type IA, or encapsulation type MA. Then when you go to zone 1, you can use flame-proof, intrinsic safety type IB, encapsulated type MB, as well as powder filling, oil immersion, increased safety type E, as well as depressurization type X or type Y. And then in zone 2, you can use encapsulated type MC, intrinsic safety type MC, pressurization type Z, as well as energy limited, which is type NL, unless you're in the United States, and it's type NC, non-sparking, which is type NA, and restrictive breathing, which is type NR. So as you can see, this gives a little bit more ability to use different protection methods if you're in a zone system versus a div system. Specifically, if you look at this, intrinsic safety is through limiting the current and the potential for energy in the area or in the device and keep that below a certain level. Typically there, we talk about intrinsic safety being the current limiting in divisions, but in zones you see there was 3 types, type IA, type IB, type IC. And type IA has the requirement that you must have double fault protection. So if you introduce 2 faults into your circuit, it still must maintain the current below a certain level. In type IB, that's a 1 fault, and in type IC, there is 0 faults allowed or present. Explosion proof in division is a heavy enclosure, sealed in a way that if there is an explosion inside the enclosure, the explosion cannot escape to the outside. Flame-proof is a similar concept in the zone system. It's not as stringent as explosion-proof. Encapsulation is a pretty straightforward thing where you're using a potting material or an encapsulating material to encapsulate the device that will keep it away from the atmosphere that you're protecting against. Powder filling is a method where we use a fine powder, typically a silica type powder, and encapsulate that around the device. What happens is if there's a spark or a flame per se at the device, the pathway through the silica is so long that the spark can't reach the outside atmosphere in a way that you could have a further degradation of the atmosphere and an explosion. Very similar to the Davy lamp. Oil immersion is using an oil principle where you actually submerge the device in oil so that you cannot have the arc present to the atmosphere. Increased safety was specifically developed in Europe, Germany as the actual country, where really what we do is we have an elevated safety coefficient that goes into the device such that you're looking at IP ratings to maintain the seal around the area, and you take extra precautions to minimize or eliminate spark potentials. Pressurization can be used in zone 1, and that's the type of X's and Y's, similarly to what we would see in div applications. When you get to Zone 2, it gets a little bit less restrictive. Non-sparking is the same as non-sparking in Division 2. Non-incentive is very similar to the energy limited, is when the hermetically sealed would be similar to restricted breathing. So what does this kind of mean if I had to wrap it all up for you? You know, some key takeaways out of this. I hope you could understand that the class zone that was introduced in the United States has brought us closer to alignment with the rest of the international community. That allows us to be a little bit more flexible and ability to place devices in mixed certification areas, as well as be a little bit more internationally competitive. The class zone allows possible protection methods that are not allowed under class div. That allows us to be a little bit more flexible in our designs, as well as to be a little bit more cost effective. And then at the end of the day, you still must use an approved protection method for the area that you're placing the device. So whether you use class div in the old school, class zone in the new school, you still must use an approved device and an approved method for the area you're using it. With that, that's kind of where we're at. I hope you found this informative. Thank you for your time and your attention, and I'll take any questions you may have.
Bruce, thanks so much for that informative presentation. We do have some questions from the attendees, so let's get right to them, shall we? The first one asks, is there a difference between flame-proof and explosion-proof enclosures?
The biggest difference comes within the length of the junction. Explosion-proof enclosures require a longer length than a flame-proof enclosure. Also, some of the bolt distances and some of the bolt requirements are more stringent in an explosion-proof application than a flame-proof application. However, in a more general sense, explosion-proof is a very specific term used in hazardous locations. Many times we will get questions regarding our ability to supply an explosion-proof device, when in fact they don't need explosion-proof, they just need a device rated for a specific hazardous location. They're unsure of what the requirements are, so they default to explosion-proof. One thing that's important to remember is when you start speaking to engineers, designers, and technical people regarding explosion-proof, you have a clear understanding of the area that you're working in and the requirements for the protection method. That will prevent these engineers, designers, and technical people from over-specifying equipment that you may not necessarily need.
Okay, Bruce, here's another question. Is any one method of protection any better than another?
Within a given area or a given zone, there is no one protection method that is considered any better than the others. What you must consider is what zone you are going in. In a Zone 2 application, any protection method for any zone is acceptable. However, in, say, a Zone 0 application, only methods that are allowed in Zone 0 can be used. But within Zone 0, as that's what we're speaking about, intrinsic safety, IA, and encapsulation type MA are both equally effective for providing device protection in that zone.
Bruce, those are all the questions we have time for. We'd like to thank you for sharing your time and your insights with us today. Now, before moving on to explore the exhibit hall of this event, please take a moment to click the Take Survey button and let Bruce know how he did today. Your feedback helps us improve the quality of our IHS Global Spec events, making them an even better investment of your time. Remember, you can see any of today's presentations during our on-demand period, but exhibitor representatives are only here on the day of the live event, so spend time with them while you can. Please experience our latest innovation, the Knowledge Exchange, offering product demonstrations and our Hot Topic podcasts. The Knowledge Exchange is also home to our event prize center, so make it a point to visit. Share your thought leadership point of view by speaking at one of our events. You can find the speaker submittal form at our event help desk in the exhibit hall. Well, we'd certainly like to thank you for choosing to spend your day with us, and we'll see you back here in the conference center a little later on.